We now look at question 6. In question 6, you are given or you are told that a light hollow ball of mass 2.6 grams and diameter 3.8 is suspended by an upward jet of air. Now the picture on the right gives you a graphic illustration of what is expected to happen. As the air moves up, it does two things. Firstly, there is a tendency to push the light hollow ball upwards, but this is balanced by a downward force due to gravity of the weight. In addition to the fact, something which is not that obvious, since the ball is in a fluid that is air, there is a buoyancy force. So we will look at the fact that there is an additional upward force in addition to the air moving upwards to create a balance between the weight down and the buoyancy upwards, so that we are able to determine the drag created by the upward thrust of air. Okay, what we need to do is we need to calculate the velocity of the air jet. And the problem is interesting in the sense that, as we will see, that there are too many assumptions and too many unknowns that we have to find some way of solving our answer. Let's get back to the solution. Now, if you look at the assumptions, we are going to assume that the surface of the ball is smooth, and we are going to use figure 15-34 in our book, which describes the drag on the either a sphere or a cylinder with respect to the Reynolds number. More about that later on. We also are going to consider the fact that the airflow over the ball is steady and incompressible. First thing we need to do in our solution is know about the properties of the air. In particular, we need to calculate the density and the kinematic viscosity of the air. Now, we get this using the fact that the air pressure is 101 kilopascals, atmospheric pressure, and the temperature is 25 degrees centigrade. Now, right, as you can see, all the data can be obtained from table A22 found on page 656 of your e-book. Let's continue. The solution unfolds as follows. The terminal velocity of a free falling object is reached when the drag force is equal to the two forces, the weight acting down due to gravity and the buoyancy which is acting in the opposite direction upwards. Okay, the formula here reveals that simple equation. and we are using the drag force formula, which is the coefficient of drag multiplied by the area, projected area, or in this case, the frontal area of the ball, and the density of the fluid, in this case air, which we have just got, density of air 1.184 kilograms per cubic meter times the square of the velocity divided by 2. Now we know the weight is mg, and the buoyancy force, the buoyancy force Fb is equal to, again, the density of the median times g times v, the volume of this light hollow ball. Okay, here is the area of the projection, which we call the frontal area of the ball, and the volume of the ball, which we need for calculation of the buoyancy force, is pi d cubed over 6. So what we do is we evaluate this. This is evaluated to give you the weight of the ball as 0.0255 newtons. Now, the buoyancy force can be calculated also quite easily, the density times g times the volume, and we get a value of 0.3000334 newtons. Now, substituting these two values, the buoyancy force and the weight, gives us the completion of the equation where the drag force, spelled out in full, is equal to the weight minus the buoyancy force. Now, the interesting situation arises is we do our computation here, which allows us to calculate the value of the velocity. And if you look very carefully here, we got all our terms, 8 times the weight minus the buoyancy force divided by pi times d squared times the drag coefficient times 1.184 to allow us to get V in terms of the 6.122 numeric value over the square root of the drag coefficient. Interesting formula because there are two unknowns. Okay? We now pause to look at figure 15.34 from your textbook. So now let's look at our solution. What we have is a Reynolds number, which we can calculate without the V. We are going to assume a velocity, and usually what we do is we assume a velocity, in some cases 10 meters per second, or in other cases we can even assume 1 meter per second. And by an iterative solution, repeat our calculation by substituting the initial value of V let us say we use 10 meters per second, we get a value of Reynolds number, and from that Reynolds number, we use our chart to find the the drag coefficient. Then we get the new Reynolds number, and we repeat the process until we get a value of velocity which does not converge. And you will find that the velocity is around 9.3 meters per second, and the Reynolds number is around 22,600. Therefore, the ping pong ball is roughly having an effective velocity, or if you put it another way, the air jet has a velocity of 9.3 meters per second. Now, in the second half, you're supposed to discuss the fact about what happens when the ball is pushed slightly to the left or to the right. Now, let's get back to the diagram. As you can see, our ball is in the center, and if we try to move the ball to the right, you will find it will not remain on the right, but it has a tendency to go back to its original position. In the same way, if we try to move it to the left. Now, what is happening? Now, this is very interesting. You find in the explanation that I have written for you, let's look at that explanation. If the ball is pushed to the side by a finger, the ball will come back to the center of the jet instead of falling off due to the Bernoulli effect. In the core of the jet, the velocity is higher and thus the pressure lower relative to a location slightly away from the jet. Any changes or perturbations in the horizontal position will force the ball back to the center of the airstream. Now, this concludes the solution. It'll be a good idea for you to re-look at this expression, substitute an initial starting value for V, okay, and then from there work out better values of V through iteration. Okay, this figure is found on page 225 of your ebook. Okay, we need this because if you look at the graph, the y-axis is the drag coefficient, the x-axis is the Reynolds number. So we need to know, first of all, whether we are dealing with a sphere or a smooth cylinder. In this case, we can consider that it is reasonable to assume that we have a smooth sphere, but we need the Reynolds number. And to find the Reynolds number, we need to know the velocity, because recall the Reynolds number depends on the velocity. Okay, if you look at what I have done, I've included the formula for the Reynolds number. But we do not know our velocity. So we are going to adopt an iterative solution.